Okay, so welcome back, everyone. Welcome to the final session of Introduction to Foundations of Generative Modeling. And throughout and today's session will be a bit of a outlier, as it suggests, because we will do generative AI with models that really does not require to create novel data, which does not need the ability to sample data. So remember that any generative model has four properties. We had properties of generative model. Sorry. Just a moment. Okay. So each of these generative models would have one of these properties that we know of. They will have one of four properties. They include, what do they include specifically? Just a moment. I think there's the okay. So this is the four properties would include novel data generation. We have discussed it in the first class. That is x sampled from p theta of x comma y, or conditional of y, whatever you want. Then we have inference, or the posterior p of y given x, which is a model prediction, clustering p theta of x automatically clusters data in the latent space. And fourth, likelihood computation. So today we'll be in particular focusing on these two ideas. There'll still be generative models, but we will say that posterior you can always compute, but we'll say that these models, today's model won't generate data, novel data. Okay, so this is the idea that today's model won't generate novel data. So we will try to make a probabilistic model. The goal is make probabilistic model giving data likelihood p theta of x, and what else? And clustering data based on high level features. For example, cluster dogs together, but separate them from cats. This is the overall goal of today's session. So if you remember, we'll do a brief recap. What is likelihood? Likelihood is the model's fit to the data. Where data is available more, it will give a larger density. Where it is not available less, it will give a lower density. It is our approximation to the underlying data distribution. So now we would want, so this is very, very important to compute likelihoods, because low likelihood data are outliers, and models should not make prediction on them. Make predictions on them. Because they are not from the training distribution, not from training data. Right. So, for example, this model, this outlier over here, but it was never in the training data. This is far removed from the training distribution. So therefore, we would never make a judgment on this. And therefore, likelihood computations are important, which tells you which data is likely to be likely in a region or not. Right. If likelihood is low, it means that that data is actually not what the model knows about. It helps you quantify uncertainties of the model, help you understand uncertainties of model. Right. So now we have seen various methods to do it. So one of them could be variational approximation, where you marginalize out the latents. Right? So this is, you can just you learn in a VAE the joint distribution of X and the data and the latents, and you can marginalize out across the latents, you're going to get the data distribution. So if you remember, we had said that, okay, so P theta of X given Z is equal to P theta of X given Z into P of Z. Right? So we say that our variational model would learn Q theta of where is it? So this model is my decoder. I already know the value of the decoder. We don't even need this. So we could just take an integral of, sorry. So we could say that the P theta of X is nothing but the integral of P theta of X given Z into P of Z dz. And you could sample a lot of data and you could pass it through the decoder, get its likelihood and take the average. So the Monte Carlo estimate is equal to 1 by n I equal to 1 to n P theta of X given Zi. Right. So from on the decoder model, this is Monte Carlo sampling, Monte Carlo estimation, where Z is sampled from P of Z. Okay. So now that is one method to do likelihoods for variational approximation. For flow methods, if you remember, we had a closed form solution. For flow method, we said that we had a Z0 and we had a list of operations F1, F2, and all the way to Ft. And this gave me the data. And when we were able to do this, make these functions invertible, so then this was clearly given by this equation of log of P of Z0 minus the sum over the determinants of the partial derivatives of all the functions, Fi's. Right? So this was one of the methods. For EBMs, we directly models to log P theta of X was, for EBMs, was directly proportional to exponent of minus H theta of X. So therefore, we get the numbers directly for GAN. So I'm revising all the methods that we did. So all the methods, VAEs, GANs, diffusion models, flow models, variation models, EBMs, and GANs. GANs, normal GANs map from Z to X through a function, G theta, the generator function. Here, likelihoods are explicit. But we have shown that under the Wasserstein distance, if we train a network FW, which takes in X and outputs a real number, this gives this min-max game, where we have this inner objective that we show over here, where you're sampling from, you're taking the difference between the scores of the, say, the likelihoods of the energy functions of the, this is the critic network, right? So we showed last day that the gradient of theta in EBMs of X is equal to, and if you take an expected value over X, Px, this is equal to X being sampled or gradient with respect to theta. With respect to theta, expected value of X in Px, H theta of X minus minus the expected value of x in q theta, or x in whatever distribution that you want, p theta of x, h theta of x. So this is exactly the same formulation that you have of the EBMs. So you try to maximize this likelihood, and you exactly get this, right? This is my EBM objective, which is equivalent to a Wasserstein-Gann objective, right? At least in terms of the theta parameters, we're trying to minimize the, remember this was the opposite sign, but it was maximization over theta, max over theta, and your Wasserstein-Gann is minimum over theta. Therefore, they're exactly the same. The critic network, therefore, actually encodes for the energy, and can be used for likelihoods. So this was a brief recap of all. And then in autoregressive models, this is the final list of models that we said. We said that the p theta of the total data distribution over time was given by the product of xi and all the history of the model. So if you take log on both sides, you'll get this log likelihood summation over all the likelihoods. So therefore, you could see that all these models primarily were developed. Although all of these models, the thing is note, although all of these models were primarily developed for, or rather, although the models were capable of computing likelihoods, they were developed primarily for sampling novel data. Primarily for sampling novel data, right? So therefore, often, if we just require likelihoods, the additional overheads of generation may not be required. So the idea is, our objective is to learn unsupervised clustering models. So you can see, I've written it over here, the unsupervised clustering algorithms, and compute likelihoods from it. So it will be a probabilistic model, having p theta of x, which is also a generative model, but we won't explicitly learn a sampler. Okay, so this will make it, this model more parsimonious and targeted to clustering and likelihood estimation, and maybe outlier detection. These models are called recognition parametrized probabilistic models. It was introduced in 2023 in a seminal paper by Walker and Sahani. So here what is done is, if you try to see the differences between RPMs and probabilistic models, it's not really very clear, but the thing that I want to take away from this is VAEs wish to reconstruct everything. everything, and hence often affected by small changes, by irrelevant changes. What do I mean by irrelevant changes? So think of these backgrounds that these dogs have, wish to reconstruct everything, and hence often are affected by irrelevant information like background. So you'll see that if there is a beach in the background, VA also tries to reconstruct the beach for the dog instead of just reconstructing the dog itself, which is the most relevant information for it. On the other hand, what we want the RPM to do is put all the dogs here together and all the cats here together separately based on high level features such as patch information. So you could patch the images up independently and then say that based on this information, these are similar. And I don't need to reconstruct the entire image back, which I was doing here, which was making this entire process of recon is not needed over here. So all I would need is based on textures or patches, cluster data and see which are more likely and assign probabilities as well. Okay, so this is the idea. So if you see the schematic I have on the left, so you could have class 1 here, class 3 here, class 2 here, and class n here. So these are all learned unsupervisedly, learned in unsupervised manner. Right, and you would know that a point inside these clusters would have high likelihood, whereas this red point, which is away from these clusters, would have low likelihood. This is the overall idea. Cluster the data, classification, and once you learn this clustering, you can use them for multiple downstream tasks. Like if you do not really know the tags of this, and later on you can just learn a linear classifier and call this a cat, you can call this a dog, because you have represented in some lower dimensional space, which is separable. Yeah, so we want is we want to do this clustering. Walker et al. Paper does it by using. So we'll say that we want this clustering, this probabilistic clustering model based on simple latents, like categorical latents. Just quickly try to understand what the data looks like. So the paper says that for this thing to work, I would divide my data X into factors. Each data point, these are called factors. So each data point, you could think of these as patches in an image. This is patch 1, this is factor 2, this is factor 3, and this is factor 4. This is one example. We'll see this in LDA, that is Latent Dirichlet Allocation, the example 1. The other example could be, say, a digit 1 and an inverted digit 1. This could be x1 and this could be x2. Both represent the same idea of 1. Right? So of the digit 1. So the idea is, like, we want to learn representations. So if I have two factors, for example, ones here, so two ones here, so it will try to put all the ones together because that's what it is going to do. So if I have two factors, so we'll come to how this model is going to do it, but anyway, so this is one example, like two ones are of the say of factors of the entity 1. So this is very important to keep this in the head. The entities is open to the user to choose. So you could choose the same category. So we'll see this in peer supervision. Or you could patch the data of an image into multiple patches and say these are the images made up of these factors. For different data sets, for example, multimodal data, you could say that audio comes from one factor, the video is the other factor, and the images is another factor. So these type of things could be done using RPMs, right? Good. So now each of these factors, what we will try to do is we will say that it's a latent variable model again. So this is a latent variable model. And we'll say that these factors, this total x equal to x1 dot 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 xj is explained by some latent. It's the latent z, which could have multiple values of latents. It could have multiple latents, right? So it could be multiple latents where each zi are typically take value between 0, 1 to k. Are typically for each zi are typically categorical. So let us take an example, and we'll be using peer supervision, and this will become very, very clear. So this idea is, if you want to take the high level understanding, it tries to say that data can be clustered based on quantized latents, quantized or categorical latents. Right? Quantize the categorical latents. So these are like, these latents will tell me, okay, this is a number one. A latent could represent just number one, and that just one value of the latent could generate the entire data of any possible ones. That's the idea. So just having z equal to 1, for example, so if you take this peer supervision over here, so this is my model. I say that I have a single z. My z is equal to, z belongs to 0, 1, 2, dot, 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 9. So here, the thing to notice is these are just tags and may not correspond to the identity of the digits. Since it is completely unsupervised. What do I mean? So I mean that I could have ones over here and have the tag of 4. So I from z equal to 4 be representing ones. I could have 4s over here and z equal to 9 be representing that. So a permutation of z's of 0, 1, 2, dot, dot, 9 will correspond to the identities, correspond to actual identities. All right. So now, so what do I mean by this? I'm saying that your z, you could have 2 or multiple of them. Your x1, x2, x3. So I will club this data of the same category and this is a single category latent. Single latent with k equal to 10 levels. Okay, so what it means is if I just have z is equal to, z 1, and if z equal to 1 maps to the digit 0, it means that this z equal to 1 just means you have generating all the types of zeros from that data. So it means it is able to cluster all the zeros together, ones together, and so on. So this one latent is going to give you idea of all the Z. So this is the graphical model. The other thing that you can do is you could have this as a, so how will we train the model? I'll come to, but that was an example. The other thing, the LDA or the latent Dirichlet allocation is the other method. Patches. Okay, so it can be seen in this figure, say all of these different patches. So this is, for example, one patch, this is X1, and they say this is equal to Xj. Right, this is X2. Different patches, non-overlapping. Okay, so I say that each of this patch, Xi, my idea here is, again, your choice of this latent, again, Z is going to total amount of Z. The total Z is going to answer this, right? I am going to say that Z is again made up of Z1, Z2 dot 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 Zj, such that Zj's explain Xj's. Right, so this is my idea. So for example, Z1 explains X1, Z2 explains X2, and all the way to Zj explains Zj, Xj. So, okay, so now there are how many latents? There are J latents. J latents. Each of them could have K categories. And they could be the same. Could be the same interpretation. Because we'll often see that the network that we'll be using to find these latents is going to be common across the factors. Could be the same interpretation across factors. So for example, if you see the rows here, K equal to 0 encodes for clouds. So if I have a latent Z and it has get 1, 2, dot, 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 10 categories. So here it is showing that K equal to 1 represents clouds, 1 represents branches. This represents some shades or asbestos, and so on. So it has learned all this implicitly. It has never been told to go and find out cluster data. So the idea is, so each of these ZJs could be explaining K factors, K textures in images. They say that there's a texture distribution. So one of them could have clouds, one of them could have houses, and so on, and then you would cluster them accordingly. So all the houses clustered together, all the clouds clustered together, and so on. So this model would do that up like on its own. So now let us try and formulate the mathematics behind RPMs, and we'll try to do the general purpose data. So the assumption that we have is, as you can see in the graphical structure, say I have a Z, and Z could be anything. So it could be made up of Z1, Z2, dot, 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 ZL, where each of them could have categories belonging to 0, 1, 2, K categories. But we're not worried about that of yet. What are the structure of Z? Let us take the entire Z, for example. The RPMs assume data to be, or the factors to be conditionally independent. Given the latents. Okay, so we are going to model the joint distribution. We're going to use variational inference again. variational inference, where we are going to model P theta of x given x comma z with joint distribution of x and z. And once we are able to model that, you can see P theta of x comma z. If you write the model of the entire joint, you can write this as P theta of z. This is the priors over z. We'll see how we'll get the priors over z into P of. And we'll see that this data will come to that will be dependent on something else as well, x given z. So now x, I said, if you see in this graphical structure, it is independent of all the factors, right? So once you get the z, given z, z factors are independent. So this is how you read a graphical model. I hope you know that from the parent, if there's a DAG, it's a directed graph, the parent explains every child node, right? So the parent is z is the parent and all the child nodes are explained by the parent, and it is conditionally independent of everything else. So now I can just say that this can be written as the product of j equal to 1 to j p theta of xj given z. Okay, so now, okay, so this is the generative model across factors. That is, given z, it outputs the patch or factor. So now I am saying that I don't want, so next step is I don't desire a generative process p theta of xj given z. So as soon as you do that, you can clearly learn a model. Instead, what we can do is we can model p theta of xj given z proportional to, or you can just say by Bayes rule, p theta of z given xj into p. We will see why I'm writing this. I will not learn this. But let us write p theta for the time being, and then we'll come back to this p theta of xj by p theta of z. Okay. So I'm just going to write this, and I'll show you what my modeling choices will be. Now, this is a classification model. Right? So given that is given z, given xj, given a patch, a factor, it outputs a distribution of z. So it's like saying that I will pass it through a neural network. If you have a single latent, I'll pass xj, and I'll get a categorical distribution of z equal to 1, whatever probability I have for category k equal to 1, k equal to 2, all the way to capital K, if you have k levels in the latent. So this is for a single latent. So this is all a model does. This is what I'll say is I will parameterize the f theta using a classic or discriminative model. Model that maps from factors to latents. So factors to latents is very simple. It's a classification problem. It is like x to z. So we are saying that, okay, once I put that value in it, if I put that in this equation, I will write this down again. P theta of x comma z, this can be written as p theta z of z of the priors into the product of j equal to 1 to j p theta of xi xj given z, which is equal to saying p theta of z j equal to 1 to j if theta of, or we will write this once again, p theta of z given xj, p theta of xj by p theta of z. So these two, you note, these will be modeled separately, not the same. So these are not the same. We do not model them in the same way. We don't model them in the same way. This is more of a prior. This is learned by the model. We'll see how. So what will I do? I'll say, based on my assumption, this will be my f theta network of z given xj. And this, I will say, is equal to this distribution, which I'll come to. This is not learned, constant. This is a delta Dirac distribution. Delta Dirac over samples, training samples, data. And I have p theta, or I will do something about this. I'll have an integral of p theta of z given xj into p0 of xj dxj. This is exactly what z is. I'm just integrating. So this is p theta of z comma xj. I'm just integrating xj out. The product j equal to 1 to j p theta of z. Okay. So now what I'll say is I will assume, this is the assumption, that pj of xj is a sample density. So this is being whatever data that I have. So in other words, it's a delta Dirac function of xj of all the samples n equal to 1 to n, 1 by n. So it is like a train of probability 1 by n into this delta function. It's a train of wherever my x1s, x1 is, x2 is, all the datas are. It's a train over delta train over data points. We also call the sample estimate of the data, a sample wise density estimate. This is very coarse density estimate, but the idea is we are not going to learn it. We'll say that wherever data exists, it is equally likely for the model to see sampling that. So that I'm saying that instead of having an underlying distribution like this, so where model, this is an underlying distribution with some probability, which is continuous for probability, and you sample from it. I am saying that if you have model points here, I will just put a delta function at these points. So it's a overfit, and it will be equally likely to sample from them. And so it's a valid probability measure, right? If you integrate this out, it will be, again, the integration of delta is 1 and at all xj's, and then you have n into n, 1 by n, which is 1. So now what will I get? So I have learned this is the delta train, and the denominator p theta of z, which will represent by capital F theta of z, is the integral of p theta of z given xj into p0j of xj. It's just marginalizing xj out in the numerator. So I'll get over all values of xj. Now this becomes tractable because this function is a delta function. I can put all the values over here. I can put the values from star. I can write n equal to 1 to n delta of xj minus xjn into the probability of or this is f theta, because we are saying we're modeling p theta by f theta. Okay. Right. So now what will happen is we know that the integral. So if you know this, that a function x delta of x minus a dx, what is it given by? This is nothing but the value of the function at a, right? Isn't it? It is like sampling. So if you have a function like this, and you have a delta function at a, so if you integrate this, the product of this, so this is like saying it is zero everywhere. It is equal to the integral of f of a x, limit x tends to the a, limit x tends to a, f of x delta x minus a dx. Because it's zero everywhere else, the function value is just going to be, you can just take the function value at this point, f of a. So you can just put the x tends to a over here, and you can take the function value which is continuous, or which exists and continuous at outside. So you'll have f of a and the integral of delta of x minus a dx over all x, which is nothing but by definition equal to 1, which is f of a. Because the function value, it is just defined at one point. So it is, if it's defined at one point, the function value will be equal to that value. Okay, so now I know this is the value at which I want to evaluate xj. So this becomes equal to n equal to 1 to n. We'll evaluate it for all the n samples because it's a summation. So this, we can take this inside. So you can write this as, we can write the summation outside, n equal to 1 to n, 1 by n, f theta of z given xj into delta of xj minus xj of n dxj, which is equal to 1 by n. So this is just putting the value of the function at the nth sample. 1 by n f theta of z given xj nth sample, right? So this is what we measured, that we write this as f theta of z, or f theta j of z, right? So now if we just put everything back into the equation, so you will get, so if you put everything back to the equation, putting everything back, this is my dagger, putting everything back in dagger, back in dagger. So we get p theta of x comma z equal to p theta of z. This is the prior. Again, writing the prior. It could be a uniform distribution, anything you want. Product of j equal to 1 to j, f theta of z given xj by f theta of z. It could be different networks as well. Pj xj. So which means that this factor is already normalized. So f theta, we need not even, f theta, it need not even be these densities, be density, as it is factor-wise normalized. So you see my f theta of z, where f theta of z is equal to 1 by n number of data points, n equal to 1 to n, if same network, right? So it's like saying I will have a network, and for each factor, I will compute the values for all the data points. I'll get f theta xj1, f theta z xjn, and I will average these average to get f theta z, right? So, and then each of these would be divided by this f theta to get a distribution, right? So this is my joint distribution, right? So this is very, very simple. So the model becomes just training this f theta network, which is going to output these distributions of over k outputs. And we'll see how we do that. But before that, let us see how to compute likelihoods. So I'll just write it at the end maybe. So I have to show that the likelihood just is equal to some constant and times some function of theta. Right. So as you can note that f theta z, it also depends. So this function also depends on the data set, because the f theta depends on data set. P depends on data set as f theta depends on data set. Capital F theta, of course. So now let us try to find out the likelihood. I think we'll have enough space to do the likelihood. So how will we do the likelihood? Say we are not assuming anything out for this. So I'll come to the specifics of the cases, and you can say this is my z, p theta, and it's for a new sample x. So you will compute the likelihood as the integral of p theta of x comma z dz, right? And since z is categorical, so you could also write this in this form. So this is p theta of z pi of j equal to 1 to j f theta of z given xj by capital F theta of into p0 xj, right? So this is a constant. So we can pull this out and we can say that it is a product over j equal to 1 to j p0 j xj, the integral of p theta of z j equal to 1 to j f theta j z given xj. So this is my function over the model. This is defined as w theta z of w theta x. And some constant. This is a constant because see, this constant cannot, it is just equal to 1 by n, right? So it will be each data point is equiprobable when you test it. If you do not have, say, if you have this strain and you're trying to find out a new data, which is somewhere here, so then this method won't work. Your likelihood will be 0. So in that case, what you can do is you can fit a Gaussian, a GMM, and estimate the likelihood, estimate the density of this. Can be estimated by fitting a GMM. That is fine. So you can take a low dimensional representation, 2 or 3 dimensional representation, and fit a GMM. Because the model always gives you a low dimensional representation, and you can fit a GMM on that. And that will give you thought of the p theta object if it is not in the training distribution at all. But that is not important, but it's mostly a constant because your data would lie in the training distribution, and often people will choose that a constant. So now let us try and understand peer supervision. Okay. So we'll try and understand what peer supervision will do. As we had said in the, so peer supervision, okay. I'll come to this, the E step and the M step, but I'll retry to write down what peer supervision is. Okay. So what peer supervision is, I have a single Z. I will have two factors or K factors. Say for now, I'm going to write, say I have J factors. Let's generalize it. Say I have, so J samples of the same entity. Okay. So now, and Z is equal to 0, 1, dot, 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 say K levels, right? It is a single latent. So as soon as you see it's a single latent, what I can do is I can do this, right? I can say that p theta of x comma z, I can write this as a single z instead of the script z over all the data set is given by p theta of z, j equal to 1 to j, and now p theta of z, this is a z, single value of z by capital F theta of z. Could have j's over here. So now this is a model that will take my xj's. It will be the same model. Mostly people use the same model. For example, this is my mnist. This is 1, 1. This is another 1. And it will pass to the same mnist and it will give me a z. And this will give me a categorical distribution of 10 values. 1, 2, 3, and all the way to 10 values, 10 categories. Because my z is 10 category latent. Okay, so if I had to calculate the, so in this case, if I have to calculate p theta of x, if likelihoods have to be calculated, so I can just do summation of, so this computing likelihoods will help you understand what these latents are. So p theta of x is nothing but summation of p theta of x and all the data, and z is equal to k because it's a categorical variable. So this becomes equal to p theta z equal to k summation of k equal to 1 to j or 1 to k, the product of j equal to 1 to j. Sorry, the summation is here. F theta j, z is equal to k given xj by f theta. So you have the same model equal to k. Right. So now once you do that, you can see that this is just like passing all these ones through the network and then seeing the probabilities of which where it belongs to. So now if a data is likely, the model would always say it would say a 1, 1 is a likely factor. Whereas 1, 2, if the model was not trained on, will have low likelihood. Because this product would be low. In one case, it will be 1, 0, 0. The other case, it will be 0, 1, 0, 0. So this product would become 0. And this product would be high if they are the same variable. That's how this peer supervision works. So that now in case, what happens here is there's this network theta learns similar representations for both factors, right? Both factors. That is, learns to clusters all factors. Learns to cluster similar digits together. Right? So your zeros would be here, your ones would be here, your twos would be here, and so on. And you could also compute the likelihoods as I showed you here. Right? So now this is what peer supervision is. It's a specific case where we have a single value of z and you have multiple factors. So now for peer supervision, what I'll do is I will show you how to train this model. So this model you can see is at the end of the day, p theta of x comma z is a variational model. It's a variational model, inference model. And thus EM comes to our mind directly. right? So let us try and write down the equations once. So we know that the elbow, we have written the elbow multiple times in the past. We know that the elbow can be written as the expected value over z being sampled from z given x log of p theta of x comma z. So here z is a single value and q of z given x. So as soon as you do this, you can write this as the expected value of over q log of p theta of z given x into p of x. Okay, just a moment. Which way can I write it? I can, this is not very useful. Instead, I can write this as x given z into p theta of z. The exact way, because I can factor out the factors, because given the latent, my data is independent, the factors are independent, right? So this is now available to me. So now I can do my KL divergence computation. I can also, yeah, I think this is much better to do this, right? So this is my elbow. This is which we have done before. This is my p theta of x. So which I can say is this is my log likelihood p theta of x minus the dkl of q theta of z given x and p theta of z given x, right? So now the idea is to have q, there's no theta here, q of z given x equal to p of or p theta of z given x, right? So this is my idea. So once I do that, this is my E step. So this is exactly the EM algorithm. My E step in the EM algorithm, the Q, the variational distribution can be equal to this. And here we can find the exact form. Here we can find exact values. And let's see how. Because I know that this is equal to P theta of x comma z proportional to x comma z by P theta of x. Right? And so as soon as I do that, I know this joint distribution. I can write this as, so this is same for all data, right? So for all, where is this? So this is the probability of z, right? So this is the same for all z equal to k, right? So I'm going to say that the probability of z being equal to the k given x is proportional to x comma z equal to k by p theta of x. It's all the same for all k, right? So now I can say that this is proportional to, so this is equal to, and therefore I can say proportional to. So this is the joint distribution, which is already known to me. Where's the joint distribution? I just now derived. So see it. So this is my joint distribution, which is what we derived just now. Okay. I can just put this value over here. Okay. This is equal to the joint distribution that I have written. So now I will, since I'm finding for z equal to k, I will put the value of z equal to k everywhere. Okay. So now if I divide this, I'll get if I have to, this is proportional to this, therefore I can write that z equal to k given x can be written as p theta of p theta z, z is equal to k, product of j equal to 1 to j, f theta of z is equal to k given j by f theta of z equal to k, divided by the summation of p theta of z, z is equal to L is equal to 1 to k categories, capital K categories, j equal to 1 to j, f theta of z is equal to L given xj by f theta of z is equal to L. So this is just the summation of all the z equal to L values. So this is my E step. I exactly know the E step. I exactly know the, what do I know? The variational distribution. Right? Which is dependent on, only dependent on f theta. So if we assume equal priors, this and this gets cancelled. If equal priors are assumed. Otherwise, you can learn the priors using a neural network and multiply the product. Some priors maybe like ones could be overrepresented if you have a biased data set and things like that. Equal priors and they would be cancelling out. And people do implement it in the RPM using equal priors for the real supervision because the MNIST data set has equal number of samples for zeros, ones, twos, threes, and all the way. So now once we're able to do the E step, now we'll do the M step. The M step we know is the theta t plus 1 is the argmax of theta, the expected value of q fixed of log of p theta of x comma z by q of z given x. Okay, so now let us write this down together. So once we're able to write this, we will be able to write it in terms of the KL divergence and we'll get a loss, right? So let us see the loss in terms of theta. Therefore, or the which you want to maximize, or the j in terms of theta can be written as the expected value over q. I can write down the joint distribution as p theta of z. I will not write down the parameters equal to k's and all. J equal to 1 to j, p theta of, or f theta of z given xj by capital F theta j. I'll do something about this, don't worry. And we'll have a denominator term q of z given x. Right? So this is my denominator term, right? So this is my, from the overall data, this is my q of z given x. This is my already computed. This is known from E step. This also is known, this also is known. Okay. So now I would have this and I will multiply this with a, I'll say I had all these j's equal to 1 to j of p theta j of xj's. So you can see that this is a constant independent of theta, and therefore I can ignore it. Ignore in the optimization. Now what I'll do is I will multiply and divide by q theta of z. So once I do that for every term in this product, if I do that, I can write this as minus of the expected value of over q log of q of z given x by p theta z plus summation of j equal to 1 to j, the expected value of over q. So I will take this together. So I can take this log of q theta of z given x, the complete x, and f theta of z, right? F theta of z plus these two terms, or rather minus expected value of q log of q theta of z given x by f theta of okay. So now as you can see, this first term becomes that dkl, negative of the KL divergence, expected value over q log of q by this. This is exactly the KL divergence between q distribution and my p theta z distribution. Then I have plus summation of j equal to 1 to j. Again, this is the KL divergence term. This is the KL divergence between my q distribution and f theta of zj. Now, if you're finding the f theta of zj's, this is theta j's. It's better to write theta j's everywhere, so it will give you an understanding. Okay, minus the dkl term of q with f theta z given xj. Okay, so this is the objective function. So you can, this is what I have to prove. Q and fj, q and small fj, and this is my regularizer with the prior learn a q close to the prior. Prior is the regularizer. So now we know. So what is dkl of q and f theta of z given xj? Similarly for other terms, for others. So this is a categorical variable. Right, this is a categorical variable. So if you have a categorical variable, what can you say? So you can say that this is we know that this is the expected value of q by f theta. So which is equal to the summation of q z is equal to k given x, j equal to this is all over j, and then this is my values of k ranging from 1 to capital K, log of q of z equal to k given x by f theta of z given xj, if I say z equal to k given xj. Okay, so you are trying to match the prediction of z equal to k with the for the jth factor with all the factors. Okay. So which is one is f theta of j and the other is the q theta of the overall distribution. So this is what you keep doing, and then this is the objective function. So if you keep doing it iteratively, you will see whatever we were trying to obtain, that the clusters of ones and twos and things like that are together, we'll be getting it easily. So now let us take the example of the last example of the latent Dirichlet allocation, where we will try to say that, again, as I was saying, each of these latents explain the data, right? And we will see that the ZJs or ZJ is again a categorical distribution. right? And given omega, this is given by omega k. So omega is equal to a number, list of numbers, say for k numbers, right? So it is a list of k numbers or such that omega I equal to 1 to k is equal to 1. So it's a distribution over, it's a distribution. It's a probability distribution. Right. So and omega's i's are omega I are greater than 0. So for the time being, what we'll do is we will think that every zj equal to k given omega is just omega k will be same. So once you're given omega, this is my probability distribution. The idea is given omega, all the latents have the same distribution. Right, so let us try and understand what does this mean, and we can write a joint probability. So my first thing to understand in LDA is my X is divided into X2 J patches. J independent patches of an image. So it is distributed, it is patched into J independent patches. And now each of this patch of the patch is explained by ZJs. So, okay, so if I write a joint distribution, the joint, so your ZZs are nothing but Z1, Z2, dot, 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 ZJ, the number of alongside omega. This is also a latent, right? And we have a fixed, we'll see what this alpha is. This is fixed. We'll come to this node later. Then this is fixed, we don't need to really worry about it. So I can write down P of X comma Z as the P theta of Z of this distribution. So again, in the same manner, P theta of X given Z, I can write this as P theta of Z, P theta of Xj given Z, J equal to 1 to J. So now Xi, Xj's are independent of all other Zs given. So P theta of Xj given all Zs equal to Z1, Z2, dot, 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 Zj from omega. This is nothing but equal to saying that P theta of Xj given Zj, right? Because you can see from the graphical structure, Xj depends is conditionally independent of everything given Zj. So if you are given this parent node here Z1, you can completely infer about X1 and you don't need information about any X2, X3, X3, omega and so on. So we know that parent node completely explains the child node. So now I can write this as, this equation will become P theta Z of Z, J equal to 1 to J, P theta of Xj given Zj, right? So now this is exactly the same equation as we did before. So this will become P theta of Z. So I will have different networks, F theta J, or the same network will do also of Zj given Xj by capital F theta of Zj, same thing, P theta of P0 of Xj, J equal to 1 to J. The difference between these two is the different model is here, difference from peer supervision, supervision is a latent structure. So latent is J comma K dimensional, latent dimension. For every patch, I have a K text dimensional texture information. Unlike in peer supervision, which was equal to 1 comma k. Z was 1D. Just one random variable. So now as soon as you do this, so this is my, so this that I have, if you can see the p theta of zj, this can be written as p theta z, z1, z2 dot 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 zj given omega into p of omega, right? So this is all these are in the, all the zj's and omega are in z. This is all the zj's, j equal to 1 to j comma omega. All these are there, and there's condition on omega. And now from the graphical structure, you can see given omega, all the zj's are independent. Given omega, all latents are independent. So this becomes the product of j equal to 1 to j p theta of z j given omega into p of omega. Okay, so the overall distribution becomes, so therefore we can write for LDA, the joint distribution p theta of x comma z, this becomes p theta z, or we can write this as the product of j equal to 1 to j f theta zj given xj, or f capital F theta zj into p theta of zj given omega, right, into p of omega given alpha. That's it. So this is fixed, therefore I'm not multiplying with, this is into alpha, this is constant. So, and I will have product of j equal to 1 to j p0 j of xj. I hope this is the correct likelihood. Joint distribution. Yes, it is. Right. So now how will you train this? The m steps remains the same. The e step, the e step is all I'll show, and the m step is just going to be the KL divergences. Similarly, the e step, I have to assume a variational distribution, right? And the variational distribution has to be assumed such that I should be a q of z given x should be assumed such that zj's j equal to 1 to j and omega can be effectively found. Okay. So now a normal choice would be, so this is my entire distribution, would be for every j, I have q of zj given xj. So this is my idea. So this is the idea. The idea is q of z given x products out to j equal to 1 to j q of zj given xj. Right? You can just multiply products of xj into p of or q of omega given alpha. Right? This can be your structure. So if this is your structure, so when you're doing the e step, they will just be equal to these numbers, right? So this will come below this, and your q zj's will come below these. And accordingly, you can multiply q theta of zj's and so on, and you will get a list of KL divergences for the maximization step. Okay, so this is the latent structure that I'll choose, and then I will equate them to p theta of zj given xj, which is nothing but f theta of zj given xj by capital F theta of zj into p theta j of xj. Right, so this I'll just equate each of them to these, and then I'll get the variational distribution if I'm assuming the product out. Right. So this is the idea. So now, so you will have texture information as I was showing of clouds and trees and branches and so on. And then you'll be able to find out the distributions or likelihoods. Likelihoods if you, for example, if it is raining and you have a fire, they would have low likelihoods. So it will learn the correspondence between these patches in the presence of an image. So it will have these texture information, similar textures together would have high likelihood and so on. Okay. So now why do we choose the Dirichlet prior is because we want, so we say that P of, you can look at what I wrote using Dirichlet distribution. P of omega given alpha is distributed as a Dirichlet distribution, or Dirichlet 0.1. So I'll first talk about the intuition and then do the math of Dirichlet. It means that if you can think of this as omega given alpha as this list of omega 1, omega 2, omega k probabilities, right? Such that omega I is equal to 1, summation of omega I equal to 1. Right, so it's a probability distribution. So having 0.1 as the parameter of this model, what it does is, if you consider 3 nodes here, so this is x1, this is 1, 0, 0, this is x2, 0, 1, 0, and this is x3 equal to 0, 0, 1. What it does is, it samples probability distributions only at the vertex. That is 1, 0, 0, 0, 1, 0, and 0, 0, 1. That is one category is selected at a time, at one time. Right? So this is the reason. So the idea is each patch must belong to only one distribution. This is the only reason that I'm going to use this 0.1 of the probability matrix of a Dirichlet distribution. So now what is a Dirichlet distribution? A Dirichlet distribution is a generalized beta distribution, which says that, so Dirichlet x1, x2, dot, 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 xk, and alpha 1, alpha 2, alpha k, these are parameters. These are random variables. Is given by is proportional to the product of xi to the power alpha I minus 1. And if you I equal to 1 to k. So if you normalize this, this is going to be the beta distribution of all the alphas, and you'll get alpha I equal to 1 to k. So if you can forget about the density for the time being, for the normalization constant across for the time being, and you can assume, you can see that if alphas are high, then what can you say? Xi's can be as high because it's a product of all these probabilities. The alpha. So for example, if Xi's are already low, powers of Xi's can't afford to be high. If xi to the power alpha I minus 1, all are symmetric. So if they are symmetric, it means that the idea is, see, xi sampling from xi is proportional to saying xi to the power alpha minus 1. So if this power is high, so these values can be high also. This is the idea. So if you can see this graph over here, this is the vertices that I have is in the cyclic order of x1, x2, and x3. So if you have 1.5, 1.5, 1.5, all of them are equally likely. And you can see that the density is inside the simplex. If you make them larger, they will try and push them away from the boundaries. And as you see, if you have 2, 2 over here, along this vertex, what would happen is, it is a very interesting thing to see. Along this vertex, so you would assume symmetricity for x2 and 3, x3, right? So as you move from 2 to 3, x2 plus x3 is equal to 1 and x1 is equal to 0, right? So what I'm trying to say is, so along this vertex, along this edge that I have on the ground here, we are going to only vary x1 and x2, and you're seeing that most of the density lies in 0.5, which means that x2 and x3 will have more sampling. Similarly, here you have alpha equal to x8, and you would see that it is all going towards x3 and farther away from x1 because that is the lowest. So the thing that I want you to take away from this is, we'll not go into the details of beta distributions. It's there in my it is there in the courses of probability. But the idea is, if you're trying to sample from a a beta a Dirichlet distribution with a very low value of alpha below 1, it all goes towards the edges, and only one of the latents categories is 1, and the rest of them are zeros, saying that your texture distribution should belong to only one category. So that's the deal, right? So each of the images that I have, or the patches that I have, should be only of one category. So what you can do is, as a homework, you can actually plot or sample from the Dirichlet distribution and plot this unit simplex using MATLAB or using Python. So you can see how the maximizing alpha i's, like sampling the alpha i's, having higher alpha i's will actually go towards, densities would shift towards those x's, which is higher alpha I. So with that, we'll come to the end of the session on likelihood. So what we learned is, these models, to compute likelihoods efficiently, we need not always have models that are capable of generation. So we can have models that can cluster data, as we have seen today, as we clustered similar objects together and we assigned probabilities to each of the objects. And we have seen that they can be used to compute outliers, find outliers, and they can be used as generalized tools for generalizable tools for any deep learning formulation where we have to cluster similar data points and use them for downstream tasks. So if you have any questions regarding this, you can always ask, and I would urge you to look into the implementation of the code. You can see it in the paper and try to change the parameters here and there and try to see if you can actually cluster zeros and ones together. Other than that, we have to end the course, and I'll be giving all the assignments. So you have to submit the assignments, and based on the assignments, you'll be getting your grades and your certificates. So please feel free to do the assignments. So there'll be some theoretical questions and some implementations. It will not be long. We'll basically have 2 assignments, and with that, we'll end the course. But what I want you to take away is, all these generative models that we learned are able to generate data, compute likelihoods, cluster data, and do all of these things with great efficacy. But when we have limited resources, which we saw today, we're also likely to be able to use models like RPMs, which would only categorize or cluster data and assign probabilities. So often probabilistic models are used to find these likelihoods when you're trying to do some classification task and want to attach likelihoods to them. So thank you for your attention and patience throughout the course. I hope you learned something, and we'll keep in touch in the Teams group. And if you have any question, feel free to contact me. I'll always be available. Thank you. See you around.